Alright, so these are the hints for homework 14. Let me put that on here. Let's see. Homework 14. Alright, so for number 2, and number 3 actually. So number 2 and 3. You're going to use this equation. The distance is equal to 1 over the parallax, and the parallax is given to you in arc seconds, and so the answer always comes out in parsecs, right? So you'll have some number of parsecs, but please change it to from parsecs to light years. And just to remind you, the way that we do that, 1 parsec is equal to 3.26 light years. 3.26 light years. Alright, and so whatever that number is, what we would do, of course, is just multiply it by 3.26, right? 3.26. And then, of course, that's 1 parsec. And the parsecs would cancel. And that gives you an answer in light years. Alright, very nice. So, here, let us clear this. Alright, for number 3, what we're going to do is, let's see, oops, sorry. For number 3, what we're going to do is we're going to use the temperature, what's called Wien's law. So the temperature in Kelvin is equal to 2.9 times 10 to the 6th divided by lambda max, or lambda peak, right? Where lambda max, of course, is in nanometers, right? So whatever this value is always given to us in nanometers. All right, and that will give you the temperature of a particular star. Let me try to draw this one again, sorry. So again, for number 7, the temperature, yeah, that looks better. The temperature in Kelvin is equal to 2.9 times 10 to the 6th divided by lambda max. And of course, lambda max is in nanometers, right? This value right here is always in nanometers. All right, that looks a little better. So sorry about that. All right, let's move on to number 8. All right, for number 8, we're going to use, and I had done an example of this before spring break. This equation is the size of a star, right? So it's R star is equal to the ratio of the luminosity of the star divided by the luminosity of the sun, or our sun, of course. We're always comparing other stars to our sun, raised to the 1/2, which of course just means, you take the square root of that ratio, so that's raised to the 1/2 power. Make sure that looks at 1/2, and then times the ratio of the temperature of the sun, which is always 6,000, of course, divided by the temperature of the star. All right, and then that ratio is squared, and then you multiply. So you multiply that. These two things come out to be just a number, and then you multiply that times the radius of our sun. And so usually answers come out like this, like it'll look like this: R star will equal some number times the radius of our sun. And of course, if the number is, if this number right here is this number right here, if this is greater than 1, then the the star is greater than the size of the sun, our sun, and then if it's less than 1, of course, it's smaller than the sun. Okay. All right, let's go on to number 11. So this is all right. So for number 11, here's the hint. This is the Doppler shift, or the Doppler effect. This is the equation for it. The velocity of something, in this particular case, it's going to, of course, it's going to be a star, is equal to. So we measure the wavelength of a particular photon. So it's the moving. So this is going to be the wavelength when the star is moving, right? So that's lambda minus what's called lambda naught. All right. So lambda naught is just the wavelength in the laboratory, and then divided by lambda naught, and then times, and then that entire thing is multiplied by the speed of light. All right, so that's how we get. All right, so let me write that. So the way lambda naught is the lab wavelength. That doesn't look very nice. Wavelength. So, sorry, this touch screen is not the best. All right. Anyhow, in other words, lambda naught is the wavelength of something that's not moving with respect to you. All right. So for numbers 12 and 13. So they both use the same equation. Actually, number 14 uses the same equation as well. So this is that equation for the combined mass. All right. So here's what it looks like. So this is when you have two stars that are in orbit, binary stars. All right. So little m plus big M. All right. So that's all that means here. So that's little m plus, you could call it M1 and plus M2. So it's these two masses. So that's what you're solving for, is the combined mass of the two is equal to, so it's just, the old style Kepler's third law, right? So A cubed, the semi-major axis cubed, which is, of course, another way of saying the average distance the two stars are away from each other, or apart, divided by the period squared. That's supposed to be a squared. All right. Yeah, that doesn't look. All right, so that's a 2. Sorry. All right, so remember, A will be in astronomical units. All right, so those of course are the units that we always use for this, and then the period for this, using Kepler's third law in this way, the period is in years. All right, so. All right, and then this combined mass is in units of what we would call solar units. All right, so little m plus big M would equal. Sorry, let me erase that a little bit. All right, so that looks a little better. Sorry. All right, so little m plus big M is going to be, some number times the mass of the sun. And that's how you leave it, right? If the number, of course, is bigger than the mass of the sun, then the combined mass is greater than our sun, which is usually the case. And then, of course, if it's less, it would be less than the mass of the sun. That is the combined mass of the two, stars that are in a binary system. All right, so like I said, number 14 is using the same equation, but it's using it in a slightly different manner. This time you're given the combined mass, that is, you're given what little m plus big M is. I think it's like 8 solar masses or something like that. So you put an 8 in there for, so in other words, this would be little m plus big M. That would equal, I think it's 8 if I remember correctly, in the problem. Anyhow, and they also give you what the period is. So I don't remember what the number is, but at any rate, you use that that for the combined mass, and so the equation becomes this, right? A cubed is equal to p squared, the period squared, which they give you in years, times the combined mass. So it's just times that whatever the combined mass is, which if I remembered it correctly, hopefully I did, that just becomes 8. All right, and so how do we solve for the semi-major axis, or solve for A? So remember, you just take the cube root of both sides, okay? So it would look like this. So A is equal to, A is equal to the cube root, right? And so you got to remember how to do that in your calculator. Remember, the cube root is raising something to the 1/3 power. That's another way of saying that. So if you know how to raise something to the 1/3 power, you can take the cube root of it. A simple way of doing this. Hold on, oops, sorry. That's. Let me erase that. A simple way of doing that is, here, let me go back to this, is like if you take the cube root of 8, right? For example, the cube root of 8 is always 2, so because 2 raised to the 3rd power is 8. All right. Anyhow, let me finish this. I'm talking and trying to draw this at the same time. Sorry about that. All right. So this little m plus big M. All right, so that's really the equation that you're going to use, right? So the semi-major axis is equal to the cube root of the combined mass times the period squared, right? There's the combined mass, there's the period squared. All right, so those are your hints. Make sure you try these. All right.